Afternoon, everyone. Great to be here. I'm just going to dive straight in, lots to get through. The topic of my talk, well, the title of my talk, I should say, is called Don't Go Changin. It'll become extremely obvious why I've called it that very, very quickly. So in 2006, Ben Moseley and Peter Marks published what turned out to be a very influential paper called Out of the Tar Pit. And in it, they address the issue of complexity in the design and the development of our software systems. And they make the separation between essential complexity and incidental or accidental complexity. Essential being the obvious, it's complexity that's inherent in the problem that we're trying to solve, whereas incidental or accidental complexity is that which isn't. They say that complexity is the root cause of the vast majority of problems in software today, including unreliability, late delivery, lack of security, etc. And that's all because our ability to understand the system is a prerequisite for all of these things. Now, according to Moseley and Marks, there's one thing in particular that inhibits this understanding. Now, they believe that the major contributor to complexity in many systems is the handling of state, and the burden this adds when trying to analyze and reason about the system. Now, the trouble is that from day one, we're taught to program in JavaScript with a very imperative, step-by-step mentality. We reassign variables, we rebind object properties and methods, we overwrite existing array indices, yada, yada. And we're taught that it's completely fine to mutate the stuff left, right, and center, but in small chunks, it's perfectly manageable, right? But there's a very, very finite limit on how much you can hold in your head at any one time. And when we start creating software of any reasonable size, these practices tend to come back around and bite us. And we end up building systems that exhibit a number of problems. So they're hard to analyze and reason about, like I've said already. You become more and more uncertain about the state of your application at any particular time in its existence. And you end up writing sprawling test suites, particularly to do with the interactions between your objects. I'm not saying it's bad to write tests, you should definitely write tests. But I think because of this rampant mutability, it lends to a limited degree of confidence in the code that we're writing. And according to Moseley and Marks, and I would go as far as to say that I completely agree that this is incidental complexity. We shouldn't need to deal with any of this. None of this is part of the problems that we're asked to solve. So Alan Kay has often compared modern software architecture to the pyramids. Yes, it's impressive, but it's really just brute force. There isn't really much of a concept here other than the fact that it'll take a lot of people hundreds of years to build. And I think it can feel a little bit like this when building JavaScript applications sometimes as well. Even if you've got frameworks that are helping you along, even they, at some point, will have had to deal with this sort of thing. Now, there are a lot of benefits, I think, to learning multiple different programming languages. Even if you never end up using them again in your life, there are still going to be concepts and techniques and new ways of thinking that you can take back with you afterwards that can help you reason about certain issues like the handling of state and hopefully in a new light. And that's what we're going to do a little bit of today. So we're going to be looking at a language called Clojure, which is a Lisp dialect. It's a functional programming language that runs on the JVM, but don't let that put you off. There's also Clojure Script, which is the compiled to JavaScript version of that language. So we're going to look at the way that Clojure deals with state management, its philosophy around handling state, and see if we can draw out some inspirations and possible solutions to reducing or ideally eliminating the complexity around state handling in JavaScript. So, object orientation as a programming model was originally conceived of as a way of modeling our programs in a way that reflects how we perceive the real world. So, by means of a comparison platform, let's use something from the real world. We'll pick a river. So in our river, the water is always flowing. The river is always changing. In OO parlance, we call this mutable state, right? And this is how we think of our objects in JavaScript. They're things that change and mutate in place over time as our systems and our apps run. And this is seen as advantageous in OO as well, right? Our objects can change, but to all observers, it's still the same object. And again, this does conform to our view of the world. If you have a cup of coffee, whether it's hot or cold, it's still a cup of coffee. Now, Clojure's view of the world is different. From that worldview, we would say that no man can cross the same river twice. When you cross the river, the water will be in a particular position beneath you. But when you cross again, you'll be wading through different water in a different position. So the key concept here is that the river is not a thing in and of itself, but it's a concept that we've applied to a set of related phenomena that are causally related over time that allows us to identify it. The same way we think about time, right? What we call time is a concept that we give to the perceived effect of a series of related transitions. But what actually exists are small indivisible entities, for example, atoms in the river's case, and the processes that then act upon them. So the change that we see in our river is not what we'd really term mutable state, but it's the result of processes being applied to something that's fundamentally indivisible and unchangeable. So let's take this worldview and run with it for a bit, and we'll look at Closure's definitions of values, identity, and state. And these are each going to build upon the previous and see what we can learn. So values, this is a pretty straightforward concept. A value is fundamentally something that does not and cannot change. If I have the number 42 and then I add 1 to it, I get 43, right? 42 has not changed when I've added 1 to it. I've taken 42, a value, composed it with another value, 1, and gotten a brand new value back, 43 at the end. Nothing has changed. It's a composite action. Now, OO languages, including JavaScript, have no real proper notions of values in this sense. There's no built-in mechanism to ensure that the objects that you're dealing with are going to be stable. And if you contrast this with Clojure, for example, the emphasis is on working on immutable values. And since these values can't change, a whole class of problem simply disappears. So Clojure also has this concept of something called identity, which identity refers to a named entity in a system that refers to a different value at different points in time. So in our river, the river as an identity refers to a sequence of changes that is being produced by some sort of process. And the head marker in Git is a perfect analogy of this. If we make another commit and then the head marker moves, we're not changing head. It's just a name. It's an identity that's pointing to a new value. So where does this leave state? Now, we tend to think of state as I think we tend to think of state as some amorphous blob of stuff that sort of reshapes every single time you poke and prod it. And apart from that, we don't really have a very clear definition of what it is. But one thing is true, that our notion of state is time sensitive. We have inextricably bound up time and state together. But Clojure, again, has a different definition to state. In Clojure, state is the value of an identity at a moment in time. It's a snapshot, and it's immutable. By its very definition, state can't change. State is not an ill-defined blob of stuff that mutates. It's an explicit snapshot of the value that an identity represents. And Clojure is very, very keen to separate this whole idea of identity from state. So the value of your objects is not the same thing as your object. Your object is just an identity, it's just a name pointing to some value, some data somewhere. An example of this, say if you've got a user model in an application, that user model, the user, is just an identity, it's a name that has been given to an object that points to different successive states of maybe stored user information over the time of your application. So Clojure says that this thing doesn't make any sense. So here are the definitions that we've got to. These are the definitions that Clojure has, that they underpin the construction of the entire language. Whilst we're here, we can actually define what we mean by change as well. If we take these three definitions of value, identity, and state, we can say that change in our applications is the movement from one state to another. But what happens if we then take these things and then apply these to objects, to our data structures? Well, we can say that our data structures are therefore a series of states over time that we attach an identity to. They're entities whose change is the movement between immutable states. It's not time-sensitive, in-place prodding. And they're structures whose state can be captured with certainty, therefore, stored and reused later without fear of change. Encapsulation of state in the way that we love to do in OO does not produce, I think, modularity and reusability. It inhibits it. If I take your object or your component and try to drop it in place of mine, but yours has got some hidden state in there, things are going to break. So can we take anything from any of these concepts and transfer some of them back across to JavaScript? So if we remind ourselves, our goal is to reduce or ideally eliminate the footprint of state change. What I think we need to do is we need to make state handling explicit. And this is what Clojure does by teasing apart these different concepts of value, identity, and state. Identities, your data structures, objects, what have you, become clearly visible as the only things that can change, and state transitions to new values become explicit and clearly intentional. So the next question is, how do we take and implement any of this? And the question that will probably follow that is, how does Clojure implement it? So in part 2, we are going to have a very quick look at 2 things that come out of Clojure that we can port across. That's the notion of purity and of persistent and immutable data structures. So first, purity. John covered this very briefly yesterday morning, but I'll just quickly go over it again. So imagine we have a function called ranstring that creates a randomly generated alphanumeric string whose length is equal to the integer we pass in, right? It's totally random, there's no seed value, nothing. If you come to test this, you very, very quickly find out that you can't even write basic assertions about this because you're going to get a different result every single time the function gets called. But if you contrast this with something like underscores map, and a function, a really simple function here called square that just takes a number of squares and returns the value, you know that given the same input, you will always, always get the same result every single time it's called. And this is the concept of purity and of pure functions. Pure functions' results are only calculated from the values of their arguments. They don't rely on data that changes outside of their control, and they cannot change the state of something external either. So having functions that rely on or change mutable data outside of them is just a recipe for complexity. And using pure functions is a very, very helpful method of program construction to use, right? And it also makes your units of code trivial to test. Now, pure functions are also values in the same way that we defined before, but not quite in the same sense as a primitive value like a number in JavaScript, for example. But if your functions will always return the same result given the same input, the function and the value they return essentially become swappable, right? And your code immediately becomes easier to reason about. Now, this might sound all a little bit limiting. After all, you know, JavaScript is a dynamic language, right? We have no strict typing system. Why would we constrain ourselves in any way? Well, I think the problem is that more often than not, we as JavaScript programmers equate the ability to freely mutate anything that's going as essential or even synonymous with the idea of dynamism. And dynamism, for our purposes, in our context, it just means a system that's characterized by constant change. But it's our definition of change that we need to reassess. Now, we know, I'd wager that nearly everyone in this room has been bitten at some point by ubiquitous mutation in applications. And we know that trying to keep a handle on it is a limiting factor, not a liberating one. So even though adopting something like purity might feel a bit constraining, I'd say that given the benefits it can yield, the pros massively outweigh the cons. Now, adopting purity is a great start, but functions need to modify their inputs, though, right? At some point, you need to take a data structure and you need to modify it. So pure functions on their own don't really help us with any of the mutability problems. And we need to bear in mind as well that any time a variable is explicitly changed, we're bundling state and time together again. And we're back in the realms of our time-sensitive programs, even if pure functions help us to keep these a little bit more controlled. But there's a second piece to the puzzle, and that's what's called persistent data structures. Now, persistent data structures have a number of properties. For starters, they're immutable. They cannot be modified in place, and this should probably sound a bit familiar now. They're values, right? They build on our understanding of state as an immutable snapshot in time. So how do we update them? We update them by creating a copy with modifications to them. So in other words, every single time we make a modification to a data structure, we get a copy and we get a brand new state. Our state change has become completely explicit and not hidden away somewhere. And what this also means is that we preserve historical versions of state with the same update and lookup complexity guarantees. So what persistence effectively means here is that we're not committing something to persistent storage like a disk. It means that we keep previous versions of the data structure. And the simplest example of this, the bread and butter of the persistent data structure world, is something called a singly linked list. Now, a singly linked list is a composite of list nodes that are just a simple pair containing a value at the head, foo, bar, baz, cucks, whatever, quucks, and the rest of the list in their tail position. So the easiest way to understand this is probably just to illustrate it. You can do it very easily in JavaScript. If you create a function here, we'll call it cons, which takes a value in a list. If we're given a list, then we're going to return a new pair with the value at its head and then a reference to the previous list in its tail. Otherwise, we're just going to return a node that only contains a value. And you might use it like something like this. We can create our initial value, stash it in list 1, extend our list with a new value using list 1, stash it in list 2, and so on and so forth, or just nest the function calls. So all we store is actually a reference to the node at the head of our list. So hopefully this gives you a bit of an idea about how you can preserve the historical states of your data structures as you modify them. This sort of structure is actually of paramount importance in Lisp languages as a whole, and the principle's the same in Clojure too, but you have much more efficient implementations of loads of different kinds of data structures that build upon this sort of abstraction. But again, we need to bear in mind that this is just an illustrative example because we still have to deal with the fact that fundamentally JavaScript data structures are mutable things. It's perfectly possible for anybody to swoop in, change a value, and then the whole rest of your data structure has been poisoned. This is the only Clojure code you're going to see, so don't panic. In Clojure, persistent data structures cannot be mutated in place. We always get back a modified version. So at the top, all I'm doing here is creating a map with 2 key value pairs, A1, B2, and stashing it in a var called myMap. If I try and associate a new key value pair of C3 with that map, I get back the modified version, but my map has not fundamentally changed. It has not been mutated. I've gotten back a copied, immutable, modified version, a new version. Yes, I am talking about Big O in one of my slides. So just briefly about performance, they're extremely efficient. Accessing an element in a Clojure structure by index is done in what's called logarithmic time, and what that effectively means is that there's very, very little difference in the amount of hops that you have to make between looking up an element in a structure containing 100 elements or 1,000,000 elements. In fact, the more the number of branches you allow your data structure to have, the quicker it gets. So you can basically look up an index of in 1,000,000 different nodes in no slower than about 6 or 7 milliseconds. Now, combined with the fact that the vast majority of Clojure uses pure functions, you can have a way of drastically reducing the footprint of state change by being explicit about all of those changes, persistent data structures, and pure functions. Okay, so all this is great for Clojure, but how does this have any relevance to JavaScript? So there's this library called Mori. Now, I mentioned before that ClojureScript is Clojure's compiled to JS version. Well, Mori is all of Clojure's persistent data structures compiled and exported for use in vanilla JavaScript in both browser and in Node. So Mori gives you a lot of really nice things, not just the structures. The API is pretty big, so I won't go through the whole thing, but you get efficient, immutable data structures. You get a uniform iteration for all over your types, including nearly all of the native JavaScript ones if you want to move between them. You get value-based equality, right? This is so nice. Even if you have 2 different data structures, if the values inside them are the same in the same order, your data structures are identical. You also get lazy evaluation and memoization, meaning that your list isn't evaluated immediately until you try and access a portion of that list. And then when you do, it's cached, so you don't perform the lookup more than once. So this is a little bit of what Mori looks like. We might create a vector object, a vector data structure rather, with the values 1, 2, 3, stash it in v1. And then we would conjoin the value 4 onto v1 and stash it in v2. And again, exactly the same as what I was doing in the Clojure example. If we look at the string representation of v2, it's got 1, 2, 3, 4, but v1 has not changed. So putting this in a slightly more applicable example, here we've got a calendar object. Hopefully that's big enough for everyone. So the appointments of our object are stored in what's called a sorted set. And this is an immutable data structure that allows you to store unique data structures inside of it, right? You cannot have more than one of the same thing in there. And it's also sorted by comparison. So this example, you can imagine we have a compare appointments function that sorts by date. Like the underlying sorted set, our calendar is immutable. Whenever we try and add a new appointment, we join it to our sorted set, and then we return a brand new calendar object with those appointments there. We can also query it for upcoming appointments, saying the number of appointments from now. So you might use it something like this. Each time we call add, you get a brand new calendar returned, but the previous historical states become maintained, right? They become preserved in this sorted set. And then we can query it saying, what are the next 2 appointments from now, and grab the titles. What this also means is it's trivial to implement something like undo. All we have to do is change the signature of our calendar to take a previous calendar version and update add as well, and then create an undo method here that just returns a previous calendar. So you can do exactly what we did here with the mycal variable over here. Remember, we've got first state, second, third. If we then call undo twice on it and perform the same query, we get a result back that would be as if we'd only added the first one. We've stepped back a couple of places. So 3-4 lines of code and we get time travel. You know, no flux capacitor necessary. So just to wrap things up, because I'm already out of time. Unchecked ubiquitous mutation is the root of all evil. There's simply no way that anyone can hold all of the complexities of state change in their heads at any one time, and we simply should need to try. It'll only get worse as our systems get larger as well. I think there's a better way to try and reason about our software, and that's by making state change explicit. In this example, you know, I've been inspired by the language whose primary design goal is to deal with the problems of sharing state. That's the whole reason that Rich Hickey went and wrote Clojure in the first place, and partially because he was sick to death of Java. Let's take values as our primary orientation. So having immutable data structures means never having to worry about mentally keeping track of what's going on. All of your value changes and state changes are explicit and apparent. And rather than having state smeared thinly across the entire program, you could isolate it from the main bulk of the code and have only a few functions that update state and do so explicitly. And ultimately, my final exhortation is, if you take nothing away from this, constantly be questioning whether the complexity you're facing is essential or it's incidental. That's me. Thank you.